In this video, we're going to do some examples using the first derivative test to find intervals over which a function is increasing and decreasing, and also find all relative maxes and mins for the function. So the first derivative test is the following. To find intervals where a function is increasing or decreasing and find relative maxes and mins, we first find the derivative f prime of x. We then find all critical numbers in the domain of f. So those are places where f prime of x equals 0 or f prime of x does not exist, but f of x is defined. We then make a number line and label all critical numbers and discontinuities of f of x on that number line over the domain of f. We test, for part 4, we test whether the derivative is positive or negative for values between the critical numbers and discontinuities. If f prime of x is positive over an interval, then we know the function is increasing over that interval, and if the derivative is negative over the interval, we know the function is decreasing over that interval. We then find the relative maxes and mins by, for any critical value. If the derivative is positive before the critical value and negative afterwards, then that point was a relative maximum. If the derivative was negative and then positive, then that point is a relative minimum. So we are going to do this for a few examples. For each of these, we're going to find the domain. Remember, that's the set of input values such that f of x is defined. So the domain is the set of values you can put in for x into f of x such that f of x is actually a number, not undefined. And we need that because if we're thinking about the intervals over which the function is increasing and decreasing and things like that, of course we're only going to be interested in intervals that are actually going to be in the domain of the function. Okay, so we want to find the domain, we want to find all the critical numbers, and we want to determine the intervals over which the function is increasing or decreasing, and find all relative maxes and mins for the function f of x, and we'll write those in the form x comma y as points. So the examples we'll do are g of x equals x to the fourth minus 4x cubed plus 4x squared, f of x equals e to the square root of x, f of x equals the cube root of x to the fourth minus 4 times the cube root of x, and f of x equals x squared times natural log of x. So please pause the video, grab a piece of paper, and try these out. We'll go through them one by one. All right, so for g of x, we want to think about the domain first of all, and this is a polynomial, so the domain is going to be all real numbers, and that's true for any polynomial because any polynomial is defined for any input value of x. There's no value for x we could put in such that g of x would not exist. Okay, now we want to find the critical numbers. And to find the critical numbers, we're going to start by finding g prime of x and figuring out where are places where the derivative either is equal to 0 or does not exist. So our derivative is 4x cubed minus 12x squared plus 8x. That's our derivative. And observe again that g prime of x always exists, is always defined. So we don't have to worry about places where g prime of x does not exist. There won't be any critical numbers of that form. So we only have to set g prime of x equal to 0 and solve for g prime of x, the derivative, equal to 0, 4x cubed minus 12x squared plus 8x equals 0. Well, it might be easier to factor some things out here. So it looks like a 4 and an x will factor out of each of these terms, and we'd be left with x squared minus 3x plus 2 is equal to 0. We can then see if it continues to factor. 4x times, if it does factor, it'll be x plus or minus something times x plus or minus something. The last term is a plus, and the middle term is a minus, so it would have to be both negatives. And yes, this will work if we do x minus 2 and x minus 1 equals 0. So a product of things is only equal to 0 if at least one of those things is equal to 0, of one of the terms. So x equals 0 for 4x, x equals 2 for the middle, and x equals 1. These are our critical values. So that was the second question we were asked. We were asked for the domain, and we were asked for the critical values. Now we want to figure out over which intervals is this function increasing or decreasing. And for that, we are going to, so increasing, decreasing, this is really just going through the first derivative test. We're going to do a number line over the domain of the function, and we're going to separate out places where the critical values are, and we are going to test points in between each of those critical values. So we can test any point that is less than 0. Picking the uneasiest point is good. -1 is usually pretty easy to plug into things. 1/2 is maybe the easiest thing to plug in here. Again, we could pick any number between 1 and 2. We could pick a third, we could pick 3/4, etc. I'm going to pick 3/2. And lastly, we need to plug in some number that is bigger than 2. 3 is a pretty simple number that is bigger than 2. So now we want to test, is the derivative positive or negative at these test points in the interval in between these critical values or critical numbers. Just a note, I keep saying critical values instead of critical numbers. They are the same thing, just different books use different terms. The book we're using right now uses critical numbers. So now we want to plug in our test points into the first derivative. So we found that our first derivative, it was a polynomial, but it also factored, and it factored into 4x times x minus 2 times x minus 1. And just as a tip, it's often easier to plug into the factored form to just determine whether a value is positive or negative, if that's all we care about, which it is here. So g prime of -1, our first test point, is -4 times -1 minus 2, that's -3, times -1 minus 1, that's -2. And that is a number, and it is a negative number because it's a negative times a negative times a negative, an odd number of negatives multiplied together. So this is a negative value. What about g prime of 1/2? Well, that's 4 times 1/2, that's 2, times 1/2 minus 2, that's -1.5, times 1/2 minus 1, that's -0.5. We've got two negatives multiplied together, give us a positive. So in this interval, we are positive. G prime of 3/2, that's 4 times 3/2, that's 12/2, times x minus 2, 3/2 minus 2, that's -0.5, times 1 minus, or times 3/2 minus 1, that's a positive 0.5. And so that gives us, well, it gives us a number, but more importantly, it gives us a negative number. It's less than 0, it's 1 negative. And lastly, g prime of 3 is equal to 4 times 3, that's 12, times 3 minus 2, that's +1, times 3 minus 1, that's +2, and that is greater than 0. Again, you could also plug into the first derivative in its non-factored form, but all we care about is whether these values are negative or positive, and so plugging it into the factored form can be easier for that goal. So this now tells us that g of x is decreasing over this first interval up to 0 because we found out it was decreasing in that test interval. So decreasing from -infinity up to 0, and it's also decreasing over here from 1 to 2, and it's increasing over the interval from 0 to 1, where we found out that the first derivative is positive, as well as the interval from 2 to infinity. So that was the second thing, or the third thing, I guess we were asked to find the intervals over which the function is increasing or decreasing. Lastly, we were asked for where the relative maxes and mins are. So we know that if the function is decreasing and then increasing, if it's a negative derivative and then a positive derivative, that is a relative min. So we've got a relative min at x equals 0, and we've got a relative max at x equals 1. So this derivative is increasing, and then decreasing, or the function is increasing and then decreasing. The derivative is positive and then negative. So we've got a relative max at x equals 1. We've got, then we're decreasing and then increasing, negative derivative, then positive derivative. So we've also got a relative min at x equals 2. So those are the x values at which we are going to have relative maxes and mins. To find the points x, y that give those maxes and mins, we need to plug in. So g of 0, this is g. So g of 0 we see is just 0. So 0, comma 0 is a local or relative minimum. G of 2 is also a relative minimum. 2 to the 4th minus 4 times 2 cubed plus 4 times 2 squared. Notice we're plugging into the original function. We're finding the output of g at that point is also a relative min. And if you do calculate that, you'll find out it's 0. So this is 2 comma 0, relative min. Okay, and last one, g of 1 is equal to 1 to the 4th minus 4 times 1 cubed plus 4 times 1 squared, and that's going to give us just 1. So 1 comma 1 is a relative max. And those are all the relative maxima and minima for this graph. Next we have f of x is e to the square root of x. So we were first asked to find the domain for each function. So the domain of e to the x is all real numbers. So just on the side, domain of e to the x is infinity to infinity, is all real numbers. E to the anything gives an output. But the domain of square root of x domain, well, we can't take the square root of a negative number, so the domain is 0 to infinity. 0 is included, the endpoint infinity is not. And so the domain of this function, the set of all input values that give a valid output that is a real number, is the half-open interval from 0 to infinity. So that is our domain. Now we want to find the intervals over which the function is increasing or decreasing, and then also find all the relative maxes and mins. To do that, we're going to use the first derivative test. So we're going to take the derivative f prime of x is, this is a chain rule, e to the something is the outside function, derivative of e to the something is just e to that something, multiplied by the derivative of the inside. Note, square root of x is the same thing, square root of x is the same thing as x to the 1/2 power. So this is, derivative of x to the 1/2 is 1/2 x to the negative 1/2. We can now rewrite f prime of x as e to the square root of x divided by, 2 is in the denominator, x to the negative 1/2. The negative brings x to the denominator, and 1/2 power is a square root. So this is 2 square roots of x in the denominator, and that is our derivative. Now we want to find the critical numbers for f, so the critical numbers, and these are places where either f prime of x equals 0 or f prime of x does not exist. So if we're talking about a function that is fractional, then the function is equal to 0 when the numerator equals 0, and one place where the function does not exist, that would be when the denominator equals 0. So we do see, looking at each of these pieces, f prime of x equals e to the square root of x over 2 square root of x. That does not exist when x equals 0, because then we'd have 2 square root of 0 in the denominator. And so therefore, the point x equals 0 is a critical number. What else? We've also got when will the derivative be equal to 0? So that's when the numerator is equal to 0. That's when e to the square root of x equals 0. And this never occurs because recall that e to the x is totally a positive function. E to the x looks like this. And so e to the square root of x, we don't know exactly what's happening there, but we know that it's always going to be non-negative. So e to the square root of x is always greater than 0. So that means that f prime of x is never equal to 0. So this is our only critical number. So that is our only critical number. That was the second thing we were asked for. Now we want to find places where the function is increasing or decreasing. And for that, we need to do a number line over the domain. Recall the domain is just from 0 up to infinity. So 0 up to infinity. And 0 is a critical number. Again, domain from 0 up to infinity. So we don't need to look at the values below 0. There are no other critical numbers like with anywhere else. So we only have one region to test. We can test any value greater than 0. Let's test x equals 1 because that's just easy to plug in. And we are going to see is the derivative positive or negative at 1. F prime of 1 is e to the square root of 1 divided by 2 times the square root of 1. And so that's e over 2, and that is greater than 0. So we see that the first derivative is positive there, and that means that the function is increasing over this interval. And there are no other places where the function could change from increasing to decreasing because this can only occur at critical values or places where the function is discontinuous. So that tells us that basically f of x is increasing everywhere. F of x is increasing over the interval from 0 up to infinity. We're having that as an open interval starting at 0, not including the point 0, because 0 is a critical number where the derivative is neither increasing nor decreasing. Lastly, are there any relative or maxes and mins? Well, we see that this function is always increasing. Because it's always increasing, that means the first point, 0, f of 0, is going to be not just a relative min, but also an absolute min, because the function begins at 0 and just increases from there. So that point 0, f of 0, is an absolute min and a relative min. Let's figure out the y value for that. F of 0, that's plugging back into the original function. The original function was f of x is e to the square root of x. So that's e to the square root of 0. That's e to the 0. Anything to the 0 power is 1. So that tells us that the point 0, 1 is both an absolute min and a relative min. There are no relative or absolute maxes in this function. Our next function, f of x, is the cube root of x to the 4th minus 4 times the cube root of x. The domain of this function is all real numbers, negative infinity up to positive infinity, because we can take the cube root of positive or negative numbers. So any number that we plug into the function has a real number as an output. In order to take the derivative, I'm going to rewrite this as x to the 4/3 minus 4x to the 1/3. And then we can use the power rule to take the derivative. So f prime of x is derivative of x to the 4/3 is 4/3 x to the 4/3 minus 1, 1/3, minus 4 times 1/3 x to the 1/3 minus 1, that's negative 2/3. Now one option is to factor some pieces out. So we could factor a 4/3 out of this. If we want to sort of get this all into one fraction, we could also factor out the negative 2/3. And if we do that, then x to the 1/3 is equal to x to the 1 divided by x to the 2/3, or in other words, that's the same thing as x times x to the negative 2/3. So factoring out a negative 2/3 leaves an x remaining from this term. Minus, well, we factored out the 4 times 1 over 3, factored out the negative 2/3, we've got a 1 remaining. And so then we could rewrite this as 4 times x minus 1 over 3 times the cube root of x squared, because that negative brings the x to the negative 2/3 down to the denominator. Okay, so f prime of x is going to equal 0 when the numerator equals 0, when 4 times x minus 1 equals 0, and that occurs when x is equal to 1, solving for x. So f prime of x is 0 when x equals 1. F prime of x does not exist when the denominator in this case is equal to 0, when 3 times the cube root of x squared equals 0, and that happens when x is equal to 0. So these are our two critical numbers. These are our two critical numbers for this function. And observe that at both of those points, the original function is defined. So while at x equals 0, f prime of x does not exist, observe that f of 0 does exist. F of 0, the cube root of 0 to the 4th minus 4 times the cube root of 0 exists. So this is truly a critical number. All right. So now we want to figure out where the function is increasing and decreasing. And to figure that out, we are going to make a number line where it is separated by the critical number. So we have a critical number at 0, we have a critical number at 1, and we are going to pick points to plug into the first derivative between those critical numbers. So any point below 0, let's use x equals -1 as a point to plug in. A point between 0 and 1, let's use x is, say, 1/2. And a point greater than 1, let's use x equals 2. And we are going to plug into f prime of x to plug into the first derivative to figure out if the derivative is positive or negative. That will tell us whether the original function is increasing or decreasing. So plugging in f prime of -1, that's 4 times -1 minus 1 divided by 3 times the cube root of -1 squared. Notice then that the numerator is going to be a negative number and the denominator is going to be a positive number, -1 squared. And so this whole thing is going to be less than 0. Again, I could calculate an exact value, but I don't need to. I just care about whether the derivative is positive or negative. F prime of 1/2, so again that's 4 times 1/2 minus 1 divided by 3 times the cube root of something squared. Something squared is always positive, so the denominator is always going to be positive here. And so we've got 4 times 1/2 minus 1, that's negative. So this is also less than 0. The numerator is negative, the denominator is positive, so this is also negative. And f prime of 2, that is 4 times 2 minus 1 divided by a positive value. 4 times 1, that is greater than 0 over a positive, so positive here. And so an interesting thing happened here. Even though 0 is a critical number, whether the function was increasing or decreasing at that point did not change. So we are decreasing, and then we are decreasing, and then we are increasing. And so this tells us that the original function, f of x, is decreasing on the interval from -∞ up to 0, and also from 0 to 1. We don't necessarily know that f is decreasing at 0 because there is no derivative. The derivative does not exist at x equals 0. So we just know from the open interval negative infinity to 0 and the open interval 0 to 1. And we also know that f of x is increasing when the derivative is positive. So on the interval from 1 up to infinity. So those are the intervals over which our function is increasing or decreasing. Now we're going to find relative maxes and mins for this function. And again, we're continuing to use this first derivative test to do this. So we see that our function is decreasing until 0, and then it is decreasing again. And so no local max or min occurs here. No local or relative max or min occurs at x equals 0 because the function is decreasing and then continues decreasing. So it's going to have values greater than it to the left of 0 and less than it to the right of 0. No local max or min. Then at x equals 1, the function changes from decreasing to increasing. So that means that 1 f of 1 is going to be a relative minimum. So we're going to have a relative min at x equals -1 because the function changes from decreasing to increasing. So let's figure out what that point is. F of 1, now we're plugging into the original function. F of 1 is the cube root of 1 to the 4th minus 4 times the cube root of 1. And so that is 1 minus 4 times 1, that is -3. And so we have that 1 comma -3 is a relative minimum. In fact, it's also an absolute minimum because the function is decreasing everywhere before that and increasing everywhere after that, except at x equals 0. So there's not going to be any point lower than the point x equals 1, y equals -3. So this is both a relative min and an absolute minimum. Okay, last one. F of x equals x squared times the natural log of x. First, we're asked for the domain, the set of all input values that give a real number as an output. So over here we have the graph not of x squared natural log of x, but just of y equals natural log of x. So remember that the domain of natural log of x is just the positive real numbers. So the domain is x greater than 0 or 0 to infinity, open interval. So that is our domain. All right, now we want to find where the function is increasing and decreasing. We want to find the critical numbers, and we want to find the relative max and min, or relative maxes and minimums, whatever happen to exist. All right, so we've already done this part. Now let's find the critical numbers. So to find the critical numbers, we're going to take the derivative, f prime of x. Here we're going to need the product rule. This is x squared times natural log of x. So first times the derivative of the second, derivative of natural log of x is 1 over x, plus the second, natural log of x, times the derivative of the first, that's 2x. And so we can simplify that. F prime of x is x plus 2x times natural log of x. Since we need to solve for x, we need to set this equation equal to 0 and solve for x. It'll be useful to factor. So this is x times 1 plus 2 natural log of x. So we want to set this equal to 0 and solve for x. This equation would be equal to 0 when x equals 0 or 1 plus 2 natural log of x equals 0. So solving this right-hand equation, that means 2 natural log of x equals -1. And so natural log of x is -1/2. And that means that x, well, we could take each side as a power of e, and that would cancel out our natural log of x because e and natural log are inverse functions. They undo each other. And so we're left with x is equal to e to the -1/2 power, or 1 over the square root of e. Okay, so this is a critical number. This is a place where the derivative is equal to 0. And this is actually not a critical number because This is not a critical number because f, it is not in the domain of f, because f of 0 does not exist. It's not in the domain from 0 to infinity open interval. So we are not interested in this point. Thus, the only critical number is x equals 1 over the square root of e. That is our only critical number. So now we can make a number line to find out where the function is increasing and decreasing. We can make a number line over the domain. So the domain just goes from 0 up to infinity. We're not interested in the values equal to or less than 0. And 1 over square root of e is here. That's our only critical number. We need to test points on either side of that interval. So for plugging in values, it's useful to know approximately what this is, 1 over square root of e. So this is less than 1. If you plug it into a calculator, you'll get 0.606 or so. It's a decimal that is irrational. But that at least helps us know what we can plug in. So we could plug in, always picking easiest numbers, we could plug in 1 is a value greater than that. And in terms of plugging in an easy number into the derivative, it's actually easier if it's something that's easy to take the natural log of. So let's do 1 over e, or e to the negative 1. That's going to be less than 1 over the square root of e. Let's use that as our other point. We could also use we could also use something like 1/2 if we wanted to. It's just up to preference. You can use any value that is greater than 0 and less than 1 over the square root of e to plug in for the lower limit. So we're plugging this in. So plug in to the derivative f prime of x to see whether the derivative is positive or negative. Again, this tells us whether the function is increasing or decreasing. So our derivative, once it was factored, was x times 1 plus 2 natural log of x. If we plug in f prime of 1 over e, that's 1 over e times 1 plus 2 times the natural log of 1 over e, or e to the negative 1. So that's 1 over e, which is a positive number, times 1 plus 2 natural log of e. Those cancel each other out, so we're just left with negative 1. So that's 1 over e times 1 minus 2, that's a negative 1. And so that's negative 1 over e, that is less than 0. So we're negative below that point. And then if we plug in 1, f prime of 1 is 1 times 1 plus 2 times the natural log of 1. So that's 1 times 1 plus 2 times natural log of 1 means e raised to what power is 1. Therefore, the natural log of 1 is 0. And so we've got 1 times 1, that is greater than 0. So this is positive over here. So that means that our function is increasing when x is greater than 1, when x is greater than 1 over square root of e, and decreasing when x is between 0 and 1 over e. So let's write that down. F of x is decreasing on the open interval from 0 to 1 over the square root of e, and increasing on the open interval from 1 over the square root of e up to infinity. So that is where our function is increasing and decreasing. Now to find relative and absolute maxes and mins, observe that our function is decreasing until 1 over the square root of e and increasing afterwards. So that means that this point, 1 over the square root of e, is going to be a relative min. In fact, it's also, again, going to be an absolute minimum because the function is always decreasing before it, always increasing after it, so it has no chance to go back down. So that's going to be both an absolute and relative minimum. There are no relative or absolute maximums. So that tells us that we've got f of 1 over square root of e. 1 over square root of e is plugging back into the original function, 1 over square root of e squared, x squared, times the natural log of 1 over square root of e. I'm going to write that as e to the negative 1/2 because it's sort of easier to think about. And so that is 1 over square root of e squared, that's just 1 over square undoes the square root, times the natural log of e to the negative 1/2. Again, those are also inverse functions, so we're just left with negative 1/2. And so we've got negative 1 over 2e, that is the output of the function at that point. And so that tells us that the point 1 over square root of e, comma, negative 1 over 2e is both an absolute and also a relative minimum.